recording. Today we are going to be discussing some more stuff associated with pumps, everybody's wonderfully favorite, pump and system curves. So what I can tell you is do pay attention, take notes, because this will be on midterm 2. You can bet your bottom dollar that. Why is this red? So sometimes they're called characteristic curves. I call them pump curves, system curves. So I will let you guys make a choice. Do you guys want to talk about pump curves or system curves first?
Pump curves.
Pump curves, all right. Pump curves and pump curve accessories. So in general, when I consider how a pump delivers head to a fluid, I can state that an increase in fluid flow rate or fluid flow through a pump results in a decrease in total head applied to a fluid. Meaning if you move the fluid faster through the pump delivers less pressure or head to that fluid. And we can define this head delivery, so delta H, as an expression that says the total head added by the pump is equal to some value A minus another value B times the flow rate of our fluid squared. And this is typically the volumetric flow rate. And so the units that you'll see more often, liters per second, gallons per minute, and these systems. Such that if I was going to graph a pump curve on a chart that shows flow rate versus the total head applied, I would have a curve that looks like this. So this would be my pump curve. And so when I think of it, how it applies to a fluid transfer system, I must also consider the impact of a system curve. Now, when I think about my system curve, what I'm really referring to is my mechanical energy balance, right? Delta P over rho plus delta U squared over 2 plus G delta Z plus work plus F equals 0. So if I'm solving for my head, right, I'd apply everything by G and I divide by gravity. And so what I'm left with is delta H equals work over G, which is equal to delta P over rho G plus delta Z plus delta U squared over 2G plus F equals my total head, right? So you guys see how I was able to rearrange the mechanical energy balance to solve for the head to be added to a fluid as it's considering our system. Now, which factors in my mechanical energy balance are a function of flow rate?
Velocity.
So velocity is a function of flow rate.
Friction.
And friction's a function of flow rate. So these are functions of flow rate. And as I can also say is these are independent of flow rate, right? If they're properly specified. So I can state that for my system, my mechanical energy balance, I have two terms, the pressure head and the static head. They're independent of flow rate. And two terms, the velocity head and the frictional dissipation, or actually this should be in terms of head loss, right? Because now we're looking at it in terms of head. And what we find is these two terms can be summarized in terms of a constant for a given flow situation. Now the constant will change. C plus, I can lump all this, I'm not going to do the derivation today, another value times the flow rate squared. And so what I'm left with is a new formal expression that shows the head required by the system. And so if I was going to graph my system on that same chart, I would show something that looks like this, where this is my system curve. And also, this is that C value, which is a combination of the net pressure to be added to the fluid between your points of interest, as well as your static head. More often than not, if you're not doing any sort of net pressure addition over your system, C will simply be the static head that's required to be overcome to get fluid to flow. So in most of the situations where we've done where delta P is 0, this essentially y-intercept is the lift that's required to get fluid to flow. And so I have my pump curve that's a negative quadratic, my system curve that is positive, a positive quadratic expression, and this intersection is known as my point of operation, which tells me if I was going to put that pump in that system, my system would operate with a flow rate here, and the pump would add this much head here, delta H. And so the question then becomes, how can I operate outside of my point of operation? Because it would be really annoying if I could only operate my system at a single point. I'd like to be able to have more control over my fluid flow. So what can I do?
Move less fluid.
So how can I move less fluid? This is a weird question, I will admit. Right? Because if I put this pump on this system, the system's going to operate where the head required is equal to the head that can be added by the pump. But I'd like to have more flexibility in my flow system beyond a single point of operation.
Change your number of pumps and
That's
how
one way to do it,
oriented?
yes. That's an expensive way to do it, but you can. And so my hint is, should I say how instead of how can I operate? How can I control flow? There's your hint.
A control valve?
A valve. Right? Because what did I say a valve did? A valve will manipulate my head loss, right? And so if I, through the use of valve, now instead of having a point of operation, I can operate in this entire region to the left. Where if I wanted to operate below that point of operation, which also can be considered the maximum point of operation. What I would do, let's say I wanted to operate here at B1. Then what you would do, the pump wants to supply this amount of head, but you only need this much head. So you put valves in place in your system such that this is the head loss associated with or the delta H of a valve, or your valves in the system. So you basically put valves in the system to drop your flow rate down by increasing the energy dissipation throughout the flow system. And so with the use of valves, now I'm not constricted to a single point of operation. I can then operate anywhere to the left of that maximum point of operation. And so to summarize, I can simply say valves allow flexible flow systems that can operate below the maximum point of operation. And so that is the key characteristics of a pump curves. Now, in general, if you look at pump curves by manufacturers, what you'll find is things are a little different. Primarily because, let's take a look at this curve here. Here, I'll see if I can do slideshow. So what you see is the total head added on the y-axis in meters and the flow rate of your flow system on the x-axis. And these are the pump curves for this system. A lot of times you can find for a given pump one of two things. You can have pumps that, and essentially a series of curves for the same pump housing with a single impeller at multiple impeller speeds, or you can have a single housing with multiple impeller sizes. The higher the impeller speed and the larger the impeller diameter for a particular pump, the more head that pump can deliver to a fluid, which is what you kind of see here. These are a series of pumps, and depending on the pump chosen and the specifications, the head applied to that fluid can change. So for example, let's see if I can draw this. How did I do that yesterday? So if I had a pump curve that looked like this, 20, and depending on where I wanted to operate, that would tell me which pump I needed to use. So for example, if I wanted to operate at a flow rate approximately 1.2 liters per second, that would give me this system here. So if I was going to operate at 1.2 liters per second, it would be this, or I should draw like this. So I would need to consider the use of pumps 5, 10, and above. Now, the closer you are to that pump operation, two things are going to happen. So for this example, if I'm looking at this system curve, which I've drawn in red, and I want to operate at this 1.2 liters per second, VM510 can be chosen. That will provide most likely the most efficient pump that you can use. However, that comes at a trade-off of being inflexible in terms of flow rate beyond that 1.2 liters per second. And so there's a trade-off between the efficiency of your equipment selection as well as the flexibility of how you can operate. So for example, I could choose 15.14. It would be inefficient in that I would need a valve to adjust for the additional head added. But if I needed to, I can operate probably up to about 1.5 liters per second in this pump without any major modification. It's so important when you're considering, design aspects of, choosing pumps, the trade-off between efficiency in the pump operation and the flexibility when as far as it comes to, modifying the flow rates as well as scale up potential. We'll talk about that a lot more, design too, and how if you're going to be limited in your scale up by your pumps, there's very little you can do besides getting new pumps. There's some things you can do to modify it, but at the end of the day, you have one of two options. You change your pump curve, which means you change your pump, or you change your system curve, which means you have to go back and look at the flow design. A couple other things that you'll see here. This system has a couple other things associated with it. One, you see this, the efficiency or the power efficiency. So for this system, this was about here. This would tell you the efficiency of that pump system would be somewhere around 60%. The power requirement would be on the order of 0.3 kilowatts. And you can also consider implications associated with net positive suction head. And one thing you'll see here is the curve on the bottom is the suction head available, or suction head required, and the top curve is typically the suction head required. So the one on the bottom, the one on the top is available, the one on the bottom is required. So usually beyond this point, this is unfeasible. So this typically tells you that far end of your pump curves you're not going to want to operate at, because then you have issues with cavitation. And so you have a homework question or two that deals with looking at pump curves. And one thing I do want to say, discard. When it comes to pump curves, one thing we have to talk about, especially as it pertains to your homework, is the considerations for pumps in series and in parallel. So if I have a single pump at a given flow rate, I know there's some head applied delta H, which follows the function that we had, right? A minus B times V squared. And so if I were to have two pumps in series, for that same flow rate, those pumps are going to apply that same delta H to that fluid. And so if I'm considering the comparison between my single pump, so V single, delta H single, this is in series, I find that each of these delta H's are the same for that given flow rate. So what you can look at is for the series situation, the flow rate for any given flow rate for single and series, the delta H applied in series is essentially N times the delta H that you see for a single pump, where N equals the number of pumps. So if you have two pumps in series, then it's just 2 times that delta H. For pumps in parallel, it gets a little trickier. Now, if I consider the flow rate, and then I look at the split, in an ideal situation, same, there's no difference between each path in the split, the flow rate will split exactly in half. However, I can't say it's a delta H going across, right? Because my expression follows this form, it's a quadratic. So I really am not sure what the head of will be applied to half of that flow. But what I can say is if I double the flow rate, then each branch will experience the delta H or the head edit that we know. Or that should be single. And so if this, for this flow rate, the delta H that I consider in parallel would be the same delta H that I consider for a single pump, given the flow rate that I consider in parallel must be N times what I see so this becomes my V parallel. Where N, once again, is my number of pumps. And I say this because it will be really helpful and critical on the homework, because I've given you some parallel and series considerations and some data. So you're going to have to take the data I provide, do some manipulation based off these equations, and what you'll find is for a given pump and a pump curve, you'll see that your single pump curve will look like this. So this is single pump. My pen will work. For pumps in series, you'll find that you're looking at the same range of flow rates, and all that means is your head has doubled for each flow rate. So this would be 2 pumps in parallel. Or sorry, in series. And for pumps in parallel, you're looking at the same range of head added, but the flow rates that you operate double. So this would be 2 pumps in parallel. And these stupid things are supposed to come to the same point. Same thing here. And so you have to consider how these pumps operate. So this will be critical for your homework this week. Now, are there any questions, comments, or things that I can clarify in how we consider pumps and system curves? I know you'll probably have more questions when you do some of the homework, but is how I've explained it clear, or are there things that are still confusing?
So on this graph, are the axes the same as the other graphs you drew? Like the y-axis is delta H and then the x is V?
Yes. So yeah, the x-axis is your flow rate, V dot, and the y-axis is your delta H. Yes. Thank you. So I could say liters per second, meters. All right. Great. We'll probably be able to look at an example on Friday. Before we kind of end for the day, I believe I left you all with a question on Monday when we were talking about net positive suction head. So to quick recap, we had stated when I'm looking at a system where the fluid is close to boiling, what happened to the pressure of the fluid as it entered the pump, and what can occur within the fluid as it enters that pump suction line. So were you guys able to come up with some good questions for that? Or answers, excuse me.
I was predicting that as the fluid approached the pump, the pressure would drop and the fluid would vaporize.
That is exactly what can happen. So for the purposes of taking those notes, going back to last lecture, I can say when this situation we had, where T was approximately T boil, the fluid pressure will decrease as it enters the pump. resulting in the formation of vapor in the suction line. This is a bad thing. And this is referred to as cavitation, where cavitation is the presence of fluid or vapor within the pump suction line. Leading to a whole slew of nasty things. It can result in pump erosion and damage. So what that means is, for any given pump, there's a certain amount of pressure head that's necessary to exist to keep cavitation from occurring. We quantify this by a value known as the net positive suction head, or NPSH, required by a pump. Now, I typically like to think of these things in terms of two values: NPSH-R, which is the required suction head as specified by a pump manufacturer, and the net positive suction head, or NPSH-A, which is determined by your fluid system. And so we can calculate NPSH-A by the expression of 1 over G times P sub A minus PV over rho minus U squared over 2 minus H sub F parentheses minus Z sub A. And one thing to keep in mind when I consider this is, one, I want to put an asterisk on the Z sub A. So this is the static head. And when I mean PV, PV is your vapor pressure of the fluid. And P sub A is typically the pressure at the top of the fluid entrance. Meaning for that system, when I look at a system like this, where T is approximately TV, P of A is here at the top. And in this instance, PA would equal to the PV, right? Because when you're at the boiling point, the pressure is the vapor pressure. And any further decrease in the total pressure results in vaporization. One thing I will note is oftentimes the velocity head term, this U squared over 2 term, is neglected from calculations because it's typically negligible. And you'll actually find in your book, if you look on page 204, equation 809, it doesn't even show up because it states that the value is pretty much minimal compared to the other terms in the expression. Another thing for that asterisk, ZA should be positive if the pump is below the fluid level. And ZA should be negative if the pump is above the fluid level. I say that because, you know, it's traditionally written as minus CA, but that negative really depends on the relative elevation between the fluid and the pump, right? So if you have net static PED being added to the fluid because it, like in this situation, this would be a positive Z sub A. But if the pump would be up and it requires a certain amount of lift to get it into the pump, then that value would be negative. Any questions on that? All right, I think that's a good stopping point. However, I do like to leave you guys with questions to consider. So the question I would leave you with this is, how can we increase the net positive suction head available in a system to avoid cavitation? So I'll leave you with that question in mind. Given the expression that we have, 1 over G times the quantity PA minus PV over rho minus U squared over 2 minus head loss, friction loss in the suction line, minus any static head changes. So based on that, what are some of the things that we can do for a given flow system to improve the net positive suction head that is available for the pump? All right, with that in mind, that is all I have for you guys today. Thank you all for a great class. I also appreciated our discussion at the beginning. It really helps as I once again consider some other things associated with future classes, this course, and how to improve and be a better instructor for you all. So thank you once again. Are there any last minute questions or thoughts before we sign off for the day?
No.
All right. Take care, guys. Have a great day.
Thank you so much.
Thank you.
Thank you.